Want to welcome everybody to the TSC Seminar Series. And our speaker today is Vincent Sitzmann, who is an incoming assistant professor at MIT EECS, where he'll be leading the scene representation group. I have never actually met you in person, Vincent, but I saw your talk at Josh Tenenbaum's group and was really impressed by the research that you're doing. Really interesting, exciting stuff. So that's why I wanted to invite you to come and speak today. And with that, so everybody should mute their microphones. I'll be monitoring the chat for any questions or anything, and I'll pause Vincent and give people a chance to ask questions if they come up. All right. So with that, Vincent, you have the floor.
Awesome. Thank you so much. Thanks also so much for the invitation. So I didn't quite know what parts of my work I should talk about, so I'm starting from the beginning. But if it turned out that someone in this audience knows that many of you are already familiar with some parts of my work, then I'm happy to skip and feel free to interrupt and ask questions. Okay, perfect. So the screen is black right now. That's intentional because everyone's sitting at their desk. That's the one advantage of Zoom lectures or Zoom talks, because I can do a little experiment with you. I'd like to ask you to close your eyes and to grasp for some object that is standing on your desk. It could be your computer mouse, or it could be your, I don't know, water bottle, mug, and lift it up. Okay, so then you can open your eyes again. Anyone who followed me in doing that little experiment is probably not surprised that you probably succeeded at picking up the object. So it seems like a very simple task. We do this all the time. But I'd like to point out for a second and appreciate that this is actually not at all a trivial task. So you're going through your life, right, with like these two eyes, which are essentially cameras. And from these two camera streams, you're constantly reconstructing and inferring a representation of the world around you that is incredibly rich. It doesn't only, in particular, encode things about the world you can see, such as color or maybe red color, but it actually reconstructs many things that you cannot see, that you have learned about the world in other ways. So for instance, when you lift something up, right, you anticipate how heavy something will be. You anticipate how hard you have to press it. And all of this you infer from vision. And how do you learn that? You learn it mostly self-supervised by like walking around, throwing stuff as a baby, like ego motion, all these things. Okay, so that's the basic fundamental insight. So what I call that thing a scene representation. So it's basically a representation of your environment that you reconstruct from vision. And these scene representations really are important if you consider for a second in basically any application of computer science that interacts with the real world, and some that don't. So in grasping, right, we just went through the steps. Obviously, it's important to know what you're grasping. You need a 3D reconstruction of the environment. In graphics, well, we want to render something photorealistically. First, we need to represent it in some manner. In physics simulations or intuitive physics, you also need to have some kind of representation of the scene before you can play through the physics. And the navigation, photogrammetry, all of these applications require representations of the underlying 3D scenes. So conventionally, we represent 3D scenes in a variety of different ways, where we handcraft the features that are stored in these representations. So for instance, in graphics, right, we usually represent a scene as a mesh, and then we have the albedo or the specular color, maybe the lighting, material properties, and we encode it in the surface of the mesh. And that's great, and it's fantastic, but it has some downsides, which is that whenever we want to solve problems with machine learning and self-supervised learning, so when we want to learn something at scale about the world, then these kind of representations are a little bit troublesome because they're usually not embedded in differentiable algorithms. They're kind of hard to infer. So it's very hard to reconstruct or parameterize a mesh via a neural network, for instance, and they don't represent all the properties of scenes that we might care about. So that's why the thing that I'm interested in is neural scene representations, which is basically studying how we can learn to reconstruct 3D scenes and how should we represent 3D scenes in the first place, such that machine learning agents can reason about them. Okay, so that's the idea. There's a few sets of requirements that we need for these neural scene representations to make sense. So they need to encode 3D structure. They need to be able to reconstruct them from incomplete 2D observations. That's really important. They need to be multimodal, so they should be possible to encode all kinds of information in these representations, and they should be scalable. So in principle, it should be possible to represent complex scenes. It should also be possible to reconstruct rather complex signals. Okay, so how could we go about ever doing something like this? So it's very hard to get supervision for all of the things you might care about. The only thing that we can really get at scale is 2D data. That's the one thing that we have a lot of, right? You could just go on YouTube, millions of people running around with a camera, collecting billions of hours of video. That's something we have a lot of. So whatever you want to do, that's kind of what we want to use for training. So the basic framework that I'm interested in one of the basic frameworks that I use in my research is looks as follows. So you take a set of 2D observations of some 3D scene, and then you have an inference step. And inference means you're reconstructing the underlying 3D scene that is underlying these 2D observations. So basically the same thing that you do when you open your eyes and you look around. You reconstruct the underlying 3D scene. So, and now how can we get supervision for this step? So how can we get supervision for 3D reconstruction? Well, we can build a renderer or a forward function. So something that goes from that scene representation back to an image in such a way that we can render out the same observations that we observed in the first place. And that will allow us to supervise this whole thing with an image loss. More generally, you can imagine, how does this connect to how us humans learn? One theory is indeed that the way we learn is, when you open your eyes as a baby and you move your head, is indeed that you basically express the belief over, okay, I'm going to move my head to the right. This is how my observations should change. And then that's how you get supervision for 3D reconstruction and things like that. So this is like an instantiation of that. And this is something that I sometimes refer to as self-supervised scene representation learning. So we want to learn representations of scenes, and it's self-supervised because we only need 2D images. Okay, so the first little step that we're going to take is we're going to think about what even is a 3D scene, and how can we describe the properties that we care about in a given 3D scene. And we're going to look at this tiny toy example here. So there's going to be a gray background, which is just tree space. Then there's these 3 objects, a circle, a square, and a blue triangle. And then there's like some arbitrary coordinate system, x1 and x2. Okay, so a very productive perspective on 3D scenes, or any kind of signal, in fact, is to model a signal as a function. So in particular, 3D scenes can be seen as functions that map 3D coordinates to whatever is at that 3D coordinate. So for instance, the room that you're sitting in can be described as a function that maps like a 3D coordinate to what is at that 3D coordinate. Like this point here is air, the desk in front of you, like all the coordinates that are in that desk should be mapped to whatever is there. And then what the feature, the thing that is that describes whatever is there, could be some high dimensional representation or feature vector. So interestingly, a classic scene representation in machine learning, or something that many people use to parameterize 3D scenes in machine learning, is a voxel grid. And a voxel grid is indeed one instantiation of that. So a voxel grid basically takes a 3D scene and cuts it into little cubes. And in every cube, you store whatever is in that cube. So for instance, if you were interested in modeling geometry, you could say all the cubes that are empty, there's like 0 in them, and every cube where there's geometry should contain like a 1, for instance, like a binary occupancy or something. And indeed, we did some work in 2018. You can use these voxel grids for reconstructing 3D scenes in a cool way and then render novel perspectives and so on. But we're not going to go into that today. Voxel grids and the reason for that is voxel grids are very expensive. So voxel grids scale with the resolution that you want to encode. And if you think about the room that you're sitting in, right? If you wanted to encode the geometry of the room at a high enough resolution to reason about small objects and so on, then the resolution you would need would be very, very, very large, and you could never store this thing in memory, and you could never work with them. So this rather classic representation is maybe not quite what we're looking for. And one other alternative parameterization that has recently gotten a lot of attention is neural fields, or neural implicit representations. And here the idea is to parameterize a 3D scene as a continuous function that maps a coordinate to whatever is at that coordinate. And we're going to take that function and we will parameterize it as a fully connected neural network. So literally imagine the room that you're sitting in. You could imagine that room would be parameterized by a neural network that maps a coordinate to whatever is at that coordinate. And we had We proposed this at NeurIPS some time ago, and we called these things scene representation networks for SRNs. Okay, so this parameterization is interesting because it can be sampled anywhere and it can be sampled at arbitrary resolutions. And that's because it's a continuous function. So you can give it any x, y, z coordinate and it'll give you something for any x, y, z coordinate where you sample it. It also parameterizes, it's also capable of parameterizing topology. And what I mean by that is it can parameterize surfaces smoothly. So if you think about, like, for instance, a point cloud, which is just points floating in space, it's not really clear where the surface is. But these continuous representations, as we will see, are capable of parameterizing surfaces. And the maybe most important thing is that the memory that these things require doesn't scale with the resolution anymore. It scales with the complexity of the scene. Okay, so let's say that was our scene representation. Now we have these two missing parts. The first is the renderer. So given a scene representation, how can we now reconstruct a 3D scene? So the renderer needs to have a few interesting properties. First, it needs to be differentiable because, as we discussed earlier, the renderer maps the scene representation to an image, and that's how we're going to supervise it. So it needs to be differentiable. We need to be able to backpropagate through the neural renderer. It needs to be rather low complexity in both memory and time because we are going to have to render images at every training step. And also important, we will not have any direct supervision of geometry. So the only supervision we will get is images. So we don't actually have any measurements of 3D geometry at all. So let's think about one way of doing that. Let's imagine this little scene here. We're going to place a camera, and now we want to render the scene from this camera's perspective. The first step here is going to be intersection testing. So for any given camera ray, we want to discover where that camera ray intersects the geometry of the scene. And the first question that arises is, how do we actually represent the geometry of the scene in this framework? So let's zoom in on the top right corner of this little square here and assume that we parameterize our scene via such a little neural network that maps a coordinate to whatever is at that coordinate. So if we looked at this little red square here, then we could zoom in and we could say, okay, so within the red square, it's going to say, well, these are like some high level feature that says I'm a red square. And then outside the red square, it could be some high level feature that says I'm free space, I'm empty. But that's not a good definition of geometry. And that doesn't really help us in finding the intersection at all. So what we're going to do is we're going to use a little trick from computer graphics. And we're going to parameterize our geometry as a signed distance function. What that means is a signed distance function maps an XYZ coordinate to the distance to the closest scene surface. So for instance, this little coordinate here is going to be mapped to the radius of this sphere, because that sphere just barely touches the surface of this red square. So this here is the signed distance. It's the distance to the closest scene surface. Similarly, this point here should be mapped to the radius of this sphere here, which barely touches the blue triangle, and so on. And importantly, the signed distance parameterizes the surfaces as the zero level set of that function. So if I give you a signed distance function, then you know that on all of the surfaces, that function will be zero. So now the problem of finding an intersection of a camera ray with the scene geometry reduces to finding the first point in the scene where the signed distance function turns to zero, vanishes to zero. Okay, so this is, so how do we now actually find these intersections? We're going to start close to the camera on the ray, and we're going to march along the ray until we find this point where the signed distance function vanishes. Naively, we could pick a constant step length and then just step along the ray. However, that would be quite expensive. And the reason for that is that you would have to choose your step length to be small enough to not actually skip any kind of geometry you might be interested in. So your step length would have to be as small as the smallest feature in your room or in your scene. That's not ideal. So maybe we can be a little bit smarter. And back then we made use of an algorithm which is known as feed tracing, which is quite smart. So you start close to the camera at this point x0. Now you're going to sample at that point x0 your scene representation, which gives you a feature that describes the local properties of the scene at that point. And now we're going to map that feature to a signed distance value. So we're going to say, okay, we're going to have a little neural network here that takes that feature and basically interprets it as a signed distance value and just gives you a number. And you say, okay, so this number here is my signed distance value. And then you're going to march along the ray according to that predicted step length. So in other words, you're using that local descriptor of the scene to predict how far you should march along the ray. So at every ray marching step, you're going to predict how far you should march. And the nice thing is, for the case of the signed distance function, once you arrive at the surface, the signed distance function is 0, so you're not going to take any more steps. And as long as you're not on the surface, you're going to predict a positive step length. So if you iterate this algorithm for long enough, you're always guaranteed to find the surface, and usually much more efficient than if you were predicting a constant, if you were using a constant step length. Cool. So we can iterate this algorithm for a fixed number of steps, and then we can say the final point where we end up for each of the rays, we're going to call that our estimate of the intersection of the corresponding ray with the surface of the scene. So the cool thing is now that the length of this ray yields a depth map. So for every ray, we know how far we marched. So for every ray, we know how far the scene geometry is away. And finally, how do we actually render the scene? The first step was intersection testing, so finding the intersection of a ray with the geometry of the scene. The second step is finding the color that we should render at that point. And for that, we're going to just sample our scene representation a final time at that final coordinate. And now, instead of interpreting it as a step length, we're going to interpret that feature as a color. And we're basically going to ask, at that point in the scene, what is the color of the scene? And we can do that for each of the rays, and then we can render out an image. And then we can compare that to our true image that we observed. And now the question is to basically fit or reconstruct the 3D scene. What we have to do is we have to find the parameters of this scene representation network such that it describes and explains all of the images. So we're going to backpropagate through our render and fit the parameters of our scene representation to the images. And it turns out that this algorithm is just differentiable, and we can do that. And it learns the geometry and the appearance unsupervised. So this was there's a question, Matt.
Hi there. So how much does your SDF network actually behave like a signed distance function? Like, is it close to linear when the distances are large, and do the objects not have accidental cavities inside?
Mm-hmm. That's a great question. So I glanced over quite a bit of detail here. So in fact, the function that we use here is inspired by a signed distance function, but actually it's something slightly smarter, because it's also actually dependent on the direction of the ray. So so in fact, I've run experiments. So in other words, it's not strictly a signed distance function. So the intuition remains exactly the same, and the sphere tracing algorithm works in exactly the same manner. But this function actually is quote unquote more useful to ray tracing, because the step length that you predict is actually larger than the step length that you could predict if you use the strict signed distance function. So it's not a proper signed distance function, in other words.
Is it well enough behaved that you could take Newton steps?
That's a good question. I have never tried that.
Because that would be as fast as you could go.
Yeah, I would have to think about that more. So like I think the fastest you could go is actually, it would be the medial
Median search?
Yeah, no, the medial axis. So like if you did, so if you knew there is actually another distance you could step, but I've never properly investigated this. But it would be interesting. Yeah.
I just mean in terms of getting quadratic convergence rate to the actual surface, if it's well behaved in Lipschitz.
Yeah, I never tried it. Would be interesting.
Okay, please continue.
Cool. So that's a great question. I should also say there's since then more work exploring signed distance functions for rendering. I'm going to have some of it later on the slide. And we also have a recent paper which is called Deep Medial Fields, which uses a slightly different formulation for ray tracing. So that might also be of interest. Cool. So now we have our scene representation and we have a little renderer. And now the question is, how do we actually get to that scene representation given a set of images? So this is the question of how do we do inference? So let's look at a simple case first. Let's look at the case where we have a single scene, but we have lots and lots of observations of that single scene. So for instance, so what that means is we will have one little neural network that maps a 3D coordinate to whatever is at that 3D coordinate. We're going to have our little renderer here, which encompasses this little thing that predicts a quote unquote signed distance value from the feature and a color from a feature. And then we have a little data set. And our data set is going to be images, in this case, of a little car. And for each of the images, we're going to have the camera perspective that that image was taken from. And now all we have to do is we have to pick a camera from our training set, render out an image of our randomly initialized neural network, compare it to the image that we have in our data set, and then just update the weights of the neural network such that it looks a little bit more like the image that we actually observed. And this is what that looks like. So here we have this little sports car, and this is actually the fitting. So you just saw it started out from like nothing, and then it converged to this little 3D reconstruction of this little sports car here. And on top, you can see the ground truth, and in the bottom, you can see novel views rendered of that car. So after we have fit the scene representation, we can just pick arbitrary new camera perspectives and render out the car from new perspectives, because we have actually reconstructed the car in 3D. And on the left-hand side, you can see the normal map, which is obtained by taking the first derivative of the depth. And as you can see, we succeeded at rendering out these novel views of this little sports car. So I was very excited back then when I got this result, because it's very cool to have like a little, neural network encode this object. And okay, but the slightly more interesting case is if we only have a single image. So let's say our whole training set was this, or like our only observation was the single image of this little car here, plus maybe the camera pose, or maybe not. So of course, you can still try to fit your little neural network to a single image, but you're not going to get anything, because this single image does not encode any 3D information in itself. So in fact, if you try to do that, what you'd see is that, and then you render out novel perspectives, you basically only get a reasonable image for exactly that camera pose that you had in your training set. And for all other camera poses, you would just get nothing or garbage, because there's no 3D information in this data set. So for that, we basically need to be a little bit smarter. And what that means is we will have to learn a prior. We will have to learn something about, in this case, the space of cars, such that from the single image, we can then say, okay, conditioned on what I know about cars, this is the 3D scene that I think we should reconstruct. And how are we going to do that? We're going to learn a space of cars. What that means is in our training set, let's say we had a data set of cars, let's say like 1,000 cars or something. For each of these little cars, we're going to initialize a separate latent code. And the latent code is just some, let's say, 256-dimensional vector, and it's randomly initialized. So for each, let's say we had 1,000 cars, now we're going to have 1,000 latent codes, and we have a mapping. We say this car belongs to this latent code. Okay, now this is what we're going to do to train our model. We're going to take our latent code, and we're going to somehow get from our latent code to the parameters of our neural scene representation. So we need something that maps the latent code to the parameters of our little neural network. And what we used back then is called a hypernetwork, which is a fancy name for something very simple. What we did in particular is we just used a neural network that takes latent code as input and just outputs all of the parameters of this other neural network. So there's no magic here. It's just takes embedding code, outputs all the weights of the little scene representation network. Okay, and now we can use our renderer again. We can render that particular scene representation from the camera perspective that we have saved. We can enforce a loss on that, and we can backpropagate the loss. Now what we do is we backpropagate the loss into the renderer, of course, but then also in particular into the weights of this hypernetwork and into the weights the latent code itself. So we're basically jointly optimizing all of the latent codes in our data set that belong to separate cars, which basically means for each car, we're trying to basically find a point in the space of cars that corresponds to that car. Now, what do we do when we get a new car? Or like, at test time, we get a single image of an unobserved object. How could we solve this problem? So we have trained our model, right? We're going to randomly initialize a new latent code, just randomly initialized. We're going to do exactly the same thing. So we're going to render out this perspective of this randomly initialized latent code. And we're going to compare that to the observation that we captured, which is going to give us a loss. But this time, we're going to backpropagate the loss only into this little embedding vector. So we're going to fix all the weights of our model. So at training time, we learned a model of cars in this case. And then at test time, we fix the weights of that model and we just ask under this model that we learned, what is the set of what is the feature vector that best describes this object that we're seeing? Cool. So, and it turns out if you do that, then you can reconstruct these objects from just a single image. So here you can see an image that was taken from kind of far away. You can see an image that is taken from up close. And this is conditioned on that you know the camera pose with respect to a canonical coordinate frame of the car. So this is an assumption you're making. So you're assuming that all of the cars are oriented in the same way, and that you know where the camera is with respect to that coordinate frame. But in that case, you can basically reconstruct these objects fairly well from just a single image. And that we're going to skip. Cool. So that's the whole thing. And you know what that gives you is you can reconstruct things from just a single image, much better than what people did before. And then it's really resolution independent because it's defined per 3D point, which means you can train it at some resolution and render it at a different resolution. So this model was trained at a resolution of 128 squared, and then you can just shoot more rays and render it at a higher resolution. You can also render out perspectives that you have actually never observed at training time. So for instance, this model has never seen a car up close. It has never seen a car on its head. Yet after you reconstructed the object, you can just zoom in and place the camera much closer or turn the object on its head. And if you try to do that with other methods that don't have this kind of 3D structure, you would find that it doesn't work. Because of course, these things are perfectly out of the training distribution. So like if your training distribution is like images of objects at a certain distance, and then you're trying to render or reconstruct an object that is much closer, you're just going to fail. But because of this inductive bias, you can generalize to these out of distribution poses. And you can also encode these like simple room scale scenes. Okay, so since we wrote that paper in 2019, there has been an explosion of amazing work on inverse graphics using these neural fields. So most saliently, there was NERF, which is a fantastic paper by Ben Mildenhall. And they, of course, like this was like very inspiring to lots of people. And the key changes and the key improvements here really were to use volume rendering instead of the sphere tracing algorithm that I described. This paper uses a volume rendering algorithm, which is a slightly different kind of ray tracing, but it's still ray marching, so it's still based on the same concept of like sampling points along a ray. They made an improvement on the network that would allow it to encode higher frequency detail, and they added view dependence. And then the important thing that really makes it work is you always are in this case of overfitting on a single scene. So this really assumes that you have hundreds of images of a single scene. And in the case where you have hundreds of images of a single scene, you can basically solve this problem of just overfitting a single neural network, and then you can render it from arbitrary perspectives afterwards. This was really inspiring to lots of people. Then there's IDR, which is priori et al., also a fantastic paper. This is really based on ray marching, like on sphere tracing, similar to what I described before. And then there's this paper PixelNerf, which also looks at the case of generalization, which is also a really great paper. But of course, there has been like so much work since then that is like a huge explosion. Yeah.
Hi. I was just wondering, like, how sensitive is the initialization of that one image, And is there a way that you can automatically figure out the pose in some manner? Because I think it's, I mean, how sensitive is it? Completely garbage that it spits out if the pose is wrong?
Great question. So, you can, let's see. So if you wanted to do pose estimation, you could certainly do that. Like, let's say you have trained your model, and then at test time you get an image of a car, and you're interested in what is the camera pose. I think you could solve that with gradient descent. More generally, however, if you wanted to do this for more complicated scenes, you are constrained by the fact that if you try to do pose estimation via gradient descent, you run into problems. It's very, very dependent on the initialization. So there's all these local minima, right? Imagine you see the car from the back, but actually you see it from the front. There's really not a way for you to get from here to there with gradient descent. It's just not going to happen.
Okay.
Yeah. So in fact, I think the most promising way to go is, like, you can take a look at Pixelnerf, which solved this in an elegant way. A promising way to go is to just actually like implicitly estimate the pose via some kind of inference network. So imagine you have a convolutional neural network or something that looks at the image and then says, basically estimates the pose of the car in a smart way. That is possible, and people have done that.
I see. Okay. Yeah.
Cool. So this is cool. So there's lots of work on these 3D structured dual seed representations, which I call these representations that are based on a function that maps a coordinate to whatever is at that coordinate. So there's like SRNs, neural radiance fields, Pixelnerf, hundreds of papers every month, I would say. Okay, so there's something interesting here that I would like to talk about. And this is, I think, quite an interesting topic, and this is something that is rather polarizing, so it's exciting. So how do these renderers all work, right? All of these renderers are based on ray marching. What that means is you have some kind of 3D representation which maps the 3D coordinate to like a feature vector or something, or whatever is at that coordinate. And now you take a ray and you sample hundreds of points along that ray, just all of them. And then each of these points you're going to map to some kind of feature, whatever is at that ray. And then you have some kind of algorithm that takes all of these features and gives you the color for that ray. So that's how all of these methods work. And like the exact algorithm changes from model to model, but that's what they're all based on. So this has a few problems. Namely, it requires hundreds of samples per ray. And it's very time and memory intensive as a result. So you can imagine that for each of these samples, you have to query your scene representation, and then you have this algorithm that has to collect all of the samples and so on. And what that means is that these methods are rather slow. So there are ways of speeding these methods up, which are very, very exciting. But what happens is that there is a trade-off of overfitting a single scene, in which case you can leverage many of these speed improvements that people have proposed, and trying to reconstruct things from limited observations. And in that case, many of these methods that people have proposed recently of accelerating this volume rendering, which are based on sparsity in some form or another, don't work very well anymore. Cool. So there's a slightly different perspective that is interesting, which is at the end of the day, what you're really interested in is the light field of the scene. And what that means is, at the end of the day, all you care about is the color of a given ray. Like, I give you a ray and I want to know what is the color of that ray. And that is known as the light field. So the function that maps every ray to the color observed by that ray is known as the light field. And we were thinking about using that as a scene representation instead. So what if we, instead of parameterizing our scene as a function that maps 3D coordinates to whatever is observed by these 3D coordinates, we represent our scene as a function that maps rays to whatever is observed by these rays. And we call that a light field network. So the basic idea is I give you some parameterization of a ray, and now you're going to take that ray and give it to a neural network, and that neural network just gives you the color. And it turns out that you can do that. In the second, I'm going to show you. In this case, it's absolutely critical to generalize across scenes and learn a prior for scenes. And we're going to see in a moment why that is the case. But this case of overfitting on a single scene is really not particularly well defined in this case. Okay, so we did this again for simple scenes, but nevertheless, it's interesting. So for these rather simple scenes, like these toy cars or something, it turns out that you can do that. So you can throw away the volume rendering, all of this 3D sampling, you can throw all of it away, and you will end up with a speed up of like a large speed up, order of magnitude speed up, because you only have to sample your neural network once per array, not hundreds of times per array. Yes. And there's a question, I think. No? Okay, then we move on. So we showed you can again like parameterize like simple scenes with this, and unintuitively, and this is something that I think is worth spending a little bit of time on just because it's very intriguing. Even though it might seem that you lose the notion of geometry, it turns out that these networks also encode the geometry of the underlying scene. And we're going to talk about how that works. So let's talk a little bit about light fields and what light fields actually do. So imagine you had this very simple scene here. So there's this like red little sphere, and there's like this black cube in the background. Okay, so now let's assume we had this blue ray here. So this blue ray went and pierced this red sphere at this point P, and you have this blue ray. Now I'm going to ask you to imagine the following. Imagine that you pick a plane that contains that ray. So this blue plane here, for instance, contains that ray. And you're going to establish a little, you are going to take two parallel lines that live on that plane, this line A and this line B. And now this ray has two intersections with this line A and this line B. One S with line A and one T with line B. So basically what these two lines do is they give you a local coordinate system for all of the rays that live in this plane. All of the rays that live in this plane, you can identify by their intersections with these two lines, except of course for the one that is parallel. Okay, so now we're going to do a cross section of the scene, and this is now the cross section of the scene along this blue plane here. Now something cool happens. So let's plot the colors of the rays at these coordinates S and T. So here's our blue ray R. I don't see it. Our blue ray R is there, let's say. So our blue ray R has an intersection S and an intersection T, and we can plot it here. It's blue. Now we can pick a different ray, like this ray here, and that ray here will be red, and it has a different S and T coordinate. We can pick another one, and we can just plot all of them in this S and T coordinate system that we established. If you do that, and if you sampled all of the rays densely, this is what you would get. So this is what we call an epipolar plane image. And the epipolar plane image has a set of properties that are very exciting. So let's talk about these. The first thing is that if you take a point in the scene, so like let's say, for instance, we pick this point P, that was the point where the ray R intersected the sphere, then all of the rays that intersect this point P lie on a line in this epipolar plane image. So these are all the pencil of rays that go through this point P, live on this green line here in the epipolar plane image. That's cool. What does that mean? The cool thing about this is that all of these rays in scenes that don't have any reflections or like specularities, all of these rays here observe the same color, right? Because all of the rays that look at the same point will all have the same color. That means that all of the points along this line will have the same color in the epipolar plane image as well. So in other words, this line here is a level set of the epipolar plane image. Now something interesting happens. Imagine the point P here moves closer to the camera or to this line A here. So we go from P here to P here. What happens is if you plot that line again, you get this line here. And if you move it even closer, you get this line here. If P was exactly on this line A, we would get a horizontal line. What this tells you is that the slope of the line decreases as the point moves closer to the camera. In other words, the slope of this line encodes the depth of the point. And all of you actually know this. It's something we deal with every day. This is basically the notion of parallax. So if you close one eye and you move your head to the left and to the right, you all know that points that are closer to you will move faster than points that are further away from you. And that is exactly what the slope of the line stands for. The slope of the line tells you how fast the point moves as you move along this line. So the cool thing now is that you can actually just take, if you look at the gradient will always be orthogonal to these lines, because these lines are level sets. So the gradient is orthogonal to these lines. In other words, the gradient of our epipolar plane image is tells you the depth of that point. Okay, so this is Matt. Yes.
I mean, there's a very restricted set of scenes in which it actually is constant color along the epipolar line, right?
Yeah, you mean scenes that don't have reflections or specularities?
Yeah, no specularities, no iridescence, and so on, right? And also you need every Lambertian surface point on the scene to be a slightly different color. Otherwise, you have multiple directions of identical color in the epipolar plane.
Yes, that's exactly right. But and I agree with you. This is like it's a very restricted set of scenes for which this is strictly true. But this assumption is exactly the same assumption that you would use for multi-view stereo. So
Agreed.
Yeah.
Agreed,
so yeah. So like
don't see many people using that stereo anymore.
Well, it's an interesting discussion. I think there's two things that are true. I think the first thing you said is completely true. It is also true that though this exact assumption is not true for any given scene, a similar relationship exists for other scenes. So for scenes where there are reflections, it's not that the epipolar plane image doesn't tell you anything anymore, right? In fact, what will happen is that the epipolar plane image will look very interesting if we have a specularity, and it's actually very easy to tell from the epipolar plane image if a certain point is a specularity or not. So sure. If you and in fact, there has not been too much work on this, which is a pity, and maybe that's because it's actually in the real world kind of hard to get these light fields and to work with them in a scalable manner. But I think it's a very interesting line of work to figure out, if I give you an epipolar plane image, or if I give you samples on the epipolar plane image, can we say things about the depth of points that have specularities, for instance? Or the way the specularity moves in the epipolar plane image tells you something about the surface normal and the position of the light. And in fact, what I would argue, and this is one reason why I'm excited about this line of work, is that when you look at it, how do you find out if something is a specularity or not? Imagine you walk around on the street and then you see a puddle. So what do you do if you want to figure out if something is a reflection or not? Well, you will stop and then you will move your head. And then you will see how does the specularity move on the surface. And given on how the specularity moves on the surface, you will make an inference on where the light source is, what the normal of the surface is, or if the surface is specular at all. So I think this is kind of the reason why I think this is interesting.
Agreed. It's an empirical question how well it works.
Yes.
As
and like
for stereo.
Yes. And I want to highlight that. Yeah. Also, I want to highlight maybe something that I want to highlight, that I'm not arguing that we should use this for estimating depth maps. That's really not my point. My point is to show that if you have the light field of a scene, then the geometry of the scene is still encoded in the light field. Unintuitively so, it's not obvious, but the geometry is still in the light field, and you can still extract it from the light field. Yeah. Cool. And in that manner, you can extract, for instance, point clouds of like simple scenes. Okay, so that's all exciting. I think we're going to skip this part because we want to talk about other things. So this works for these simple scenes, and it has a set of, maybe we can talk about limitations for a moment. In the current formulation, this is constrained to parameterize mapping one ray to one color. So for instance, if you had this ray here right now sees the blue sphere, but the light field networks as they are formulated right now cannot parameterize both of these, the colors of both of these rays, because from the light field network's perspective, both of these rays are actually the same ray, and both of them have to be mapped to the same coordinate. So this is a current limitation. And then it's not generally as multi-view consistent as a 3D representation would be. And in fact, the multi-view consistency of these light field networks is connected to how well your reconstruction worked. So if your reconstruction works really well and you do a good job at reconstructing a given scene based on your prior, then your light field will also be multi-view consistent. But if you have failed to reconstruct a given scene because your prior was not good enough, then your light field will also not be multi-view consistent. Okay, so I want to briefly talk about something that we have recently that is not yet published, but and I'm only going to talk briefly about it because at the end of the day, as you might have noticed, like right now, these methods are all constrained to rather simplistic scenes. At some point, of course, we would like to go to real-world scenes and be able to reconstruct real-world scenes with these methods and train these at scale. And there has been some work recently that is going in this direction. So that's exciting. I think we will get there in the near future. But for now, there's one important question that is unsolved: is what if scenes are compositional? So if you look at this scene here of an airplane, you can see all of these chairs. And as a human, you know that all of these chairs are basically an instance of the same kind of object. You know, there's like 300 chairs in this airplane or so. And you have no trouble imagining the 3D structure of one of these chairs and realizing that they're basically copies of each other. So how could we build a model that does the same thing? So right now, in the models that we have discussed so far, one scene or one 3D scene is encoded in this like one little vector. So it's a monolithic representation. And that actually leads to problems if you have scenes that are composed of many different things. And the reason for that is that scenes that are composed of things have very many degrees of freedom. Imagine in your training set, imagine you have a room with 5 different objects. That room has lots of degrees of freedom. You can take one object, place it, and then you can place the second one anywhere. And then you can take the third one and you can place it again anywhere. And so it's very unlikely that in your training time, you have seen all of the different configurations of a given scene. And that is, however, what machine learning systems are based on. More or less, they do interpolation of your training set. So if you do the naive thing and you try to learn one manifold that tries to parameterize these compositional scenes, you're going to have a bad time because your samples in this very high dimensional space are so sparse. So and one solution to this is object-centric representation. So imagine that instead of parameterizing the whole scene as one little vector, you say for each of the objects, we're going to parameterize each of the objects in the scene as a separate vector. And then your neural network has a much easier time because it only has to learn these latent spaces of single objects. We're going to talk about this briefly because I don't know how much time we have left. 9 more minutes, is that right? Okay, so then I'm just going to skip this and just go to the results. This is kind of cool. It's still constrained to simple scenes, but long story short, each of these little objects is actually represented as a light field. And you can just train on images of scenes. So there's no segmentation masks, there's no labels except for images. And just from images, this model actually learns object-centric representations. And at test time, you can take a single image and it will be parsed into its components. And subsequently, you can render it from novel perspectives and zoom in. And you can do things like, take objects, you can delete them, you can move them around. And this is done from a single image, and it's very efficient to render and it's very efficient. So what we're currently working on is basically taking this and making it run on more complex scenes than this, and we're making progress towards that, which is exciting. Okay, so this I already talked about. So briefly, I want to talk about something else, which is this notion of, which is that there is an idea here which is actually more general than just 3D scenes. So far we talked about 3D scenes, and we said, well, a 3D scene can be parameterized as a function that maps the 3D coordinate to whatever is at the 3D coordinate, or as a light field, which maps a ray to whatever is observed by that ray. This notion of a field, of a function that maps a coordinate to whatever is at that coordinate is, of course, much more general. In fact, you can imagine images can also be parameterized as fields. So an image is a function that maps a 2D coordinate to whatever is at that, whatever color is at that 2D coordinate. A point cloud, that's a 3D shape. We kind of already talked about that. But an audio signal is the same. You can parameterize an audio signal as a function that maps a 1D coordinate to the amplitude at that 1D coordinate. So what's interesting is that currently that's not how we parameterize signals. We generally always parameterize signals as discrete samples. So images are pixels, audio signals are discrete samples of amplitudes, and so on and so forth. So this notion of a neural network that parameterizes a function can be applied to these things as well. So we've already seen how you might do that with shapes, which is by assigned distance functions, which was proposed by these folks here in 2018, which was very inspiring. What we were interested in is, after our work on scene representation networks and some other things, was, well, how could we, can these functions even parameterize more complex scenes than the thing that you just saw? So is it even possible to parameterize something like a whole room scale scene with these representations? And we tried doing the same thing for like this point cloud here. So you take this very detailed point cloud of this room scale scene, and you try to fit a ReLU neural network to the zoom scale scene, and you'd find it doesn't work at all. It'll look like this. So it turns out that's true for all other kinds of signals as well. So if you try to fit images, that also doesn't work. It gives you just this blurry mess. If you try to fit audio signals, that also doesn't work. And something that we're not going to talk about much, but something that I found very interesting back then was that there's many signals in the real world that are defined via differential equations, such as wave propagation. And our world is physics. Differential equations are the language of physics, but for differential equations, it's really important that the function that you use to parameterize the solution has well-defined derivatives. Because if your differential equation is defined as a function of derivatives, but your neural network doesn't have a second derivative, then that's bad news. And it turns out for ReLU neural networks, ReLU neural networks, for instance, don't have a second derivative. So that's not good. So we had this paper called Siren, which we called sinusoidal representation networks, which is based on a very simple idea, which is we're going to take the ReLU unit and replace it by a periodic sign. And it turns out that if you do that, then you can fit all of these signals perfectly. So we demonstrated this for images. So you can parameterize an image as a continuous function by a neural network. You can fit this room scale scene, the signed distance function of this room scale scene by a neural network, audio signals, and you can also solve partial differential equations in this manner. And the intuition for why this works is twofold. If you think about a ReLU neural network, a ReLU unit really only does something interesting at its kink. So ReLU unit is 0 when it's negative, right, and linear in the positive domain. And the only interesting thing really happens at the kink. If you replace the ReLU with a sign, the sign does something interesting over the whole input domain, and it can basically replicate its activation across the whole input domain. And the second thing is this point about derivatives. If you have a ReLU neural network, the first derivative is piecewise constant. The second derivative is 0 everywhere, except for at the origin where it's undefined. While the derivative of the sine is the cosine, and the derivative of the cosine is the sine again. And it turns out that by doing a little bit of math, you can then solve very simple partial differential equations via just backpropagating into this neural network via gradient descent, which is kind of cool. And you can also parameterize these very complex large-scale scenes with just a single neural network. So in fact, this is a neural network with 5 layers and like 512 hidden units, I think. It's tiny, tiny. I think it's 2.2 megabytes, and it encodes this whole room scale scene. And on the right-hand side, you can see Siren, and on the left-hand side, you can see a ReLU neural network. And this really works really well. And since then, a lot of people have investigated using these representations for compression or for all kinds of things. In fact, there's one application that people are very excited about is 3D GANs, so 3D generative adversarial networks. I'm sure you've seen some of this, but even StyleGAN v3, which is just the state-of-the-art 2D image GAN, is actually such a neural field. So StyleGAN v3 is a function that maps a coordinate to a pixel color. It's not a convolutional neural network. There's no StyleGAN v2 used to be a convolutional neural network. We're gone. That's all gone. No more convolutional neural networks. State-of-the-art GANs are almost exclusively based on these neural fields that are continuous functions that map pixel coordinates to colors. And we have a review paper on this, which is called Neural Fields in Visual Computing and Beyond. This class of functions is called neural fields. Okay, I fear we won't have time to talk about the last part in detail, but I'm just going to tell you what it does. So this is a very recent work where we use these neural fields and these neural scene representations for robot manipulation. So the objective is you show a robot a set of tasks, such as taking a mug and placing it on this rack here. So you give the robot a mug, you show it the task once, and then the task is I give the robot a new mug that it hasn't seen before in an unseen pose, and can the robot replicate the task that you just demonstrated to it from few demonstrations. The objective really is show the robot 7 times, and then from these 7 times, can you do it with new mugs in unseen poses? And that's the problem we solved. We don't have time to go into it. The paper is called Neural Descriptor Fields. It's quite cool. I'm happy to talk about it offline at some other point in time. Yeah, this is cool. So basically, I think we can wrap up. 1 second. There's many slides. We would have never gotten through that, I guess. Okay, this is too slow. Let's try this again. Aha, cool. So let me share screen. Here we go. Okay, so to sum up, the thing that I'm most excited about is perception. And if you look at this image here and think about what the problem is that computer vision is currently solving, we're really, really far away of getting to anything that is close to what you do when you look at that image. What you do when you look at that image is really reconstructing the underlying scene. And I don't mean photorealistically or something like that. What I mean is really in the sense that we did when you solved that little problem at the beginning of this talk where you picked something up. When you look at this image, you do inference on all of these properties of the scene that you can't actually observe. You can imagine what it would feel like if you walked over the grass barefoot, right? You can infer that it's a sunny day because you can see shadows on the grass, right? You can infer that there's trees that you can't observe, but you still know because you can see the shadow. You can think that the little dog is looking somewhere off the camera, something has caught its attention. You can think about how far the dog is away from the camera, how big it is because you can see the little tennis ball. So you really do something that is more similar to reconstruction of the scene than it is to saying this is a dog or semantic segmentation or doing any of these other classic computer vision problems. And that's really what we want to get to. We want to be able to just from looking at video and looking at unstructured signals, learn about properties of the world that we cannot get supervision for. And there's an infinite number of interesting things to do there. One very interesting thing is also related to the discussion we had earlier, actually. When you watch this little video, you're going to see in a second the reflection of the gentleman who's capturing this video in the car. So you can actually already see it kind of here. So, when you watch this video, you immediately know that this is not a tiny human, which is like crumpled up and like 2 meters away from the camera, right? You know that what you're seeing is a reflection. And you can actually, from that reflection, tell quite a bit about the pose of the human, the 3D geometry of the scene, and so on and so forth, even though this video is extremely under constraint. Even just from this still frame, you can infer the geometry of the underlying scene, even though there's all of these heavy specularities and so on. And how to do that is really an open question. Like one approach that many people are interested in is like trying to go more down the computer graphics route, like solving this with multi-bounce ray tracing, for instance, right? You try to just model reflections by shooting array and then generating secondary rays and so on. But that's probably not what your brain does, right? When you look at this image, your brain isn't running its little ray tracing engine and like bouncing around millions of rays to figure out that this human is standing in front of the car. So this is an interesting question. And then there's lots of problems in robotics and physics, of course. And long story short, this is all very exciting. These are some of my collaborators. I want to really highlight the students that worked on some of these projects. So, for instance, Cameron and Coven worked on the project of compositional light fields. If you get the chance to work with any of these people, I highly encourage you to do so. They're all really, really fantastic and amazing. And that's the end of my talk. Thank you so much.
Thanks, Vincent. Very, very interesting work. Really great, exciting, interesting body of work.
Thank you very much. I think I have to cut down a little bit on this. I'm sorry if it was too rushed. I'm still figuring out like what to talk about and what not to talk about since these new projects are coming in.
Yeah, it's good to have too much. Basically says you're being prolific.
Yeah.
The cup demo was particularly exciting.
Yeah, I think I'm going to cut down on some of the earlier stuff to talk about the robotics application more, because the robotic application is really exciting. And I think there's going to be a lot of development over the next few years in using these kinds of 3D representations in robotics, because lots of robotics these days is done either from assuming quite good access to geometry, or from images, and then training something that directly operates on images. And I think this notion of having a 3D reconstruction first of the scene and then operating on top of that 3D reconstruction is going to be extremely impactful.
I agree. I mean, one of the things that I've emphasized with the group for now years is that these pixels are just an intermediate representation of things in the real world. And you know, things that make no sense in 2D, like occlusion, make perfectly good sense in 3D. We're at a little bit of a disadvantage in a lot of ways because, of course, a baby, human, any animal, anything has stereo and therefore 3D vision. So the first thing I think that people attend to primarily is shape. And so, and you have sort of segmentation for free by 3D and depth perception. And when we start with computer graphics, we don't get any of that. We got to sort of build it in somehow after the fact. But I think your approach is really good.
Well, actually, Dan, or Alan, I challenge that. The only critters that come with a depth perception out of the box are carnivores. You know, the herbivores like deer and such typically have very little 3D. They have very little overlap in their depth zones.
Yeah, but of course, you know, motion parallax gives you depth cues, and I mean, even people with one eye can see 3D. We're kind of built that way.
Yeah.
And sort of, if I just give you a flat 2D image, it's hard to understand the world unless you understand the world in 3D. So
That's true. Motion parallax does a lot.
yeah.
There are lots of foraging birds that have 2 retinas per eye, and therefore can conceivably do stereo in one eye. That's also true with some crustaceans.
Oh, interesting.
Oh yeah,
and octopodes.
The sawtooth retina, or the sawtooth cornea, not cornea, iris.
Iris for for octopodes.
Yeah, there's actually go for it.
I was just going to say, I think goats probably have the same thing because they've got those 2 openings on the eye.
Yeah. So actually, can I ask another question? I've been monopolizing the speaker. So a lot of this, the early stuff is essentially an argument that it's easier to use differentiable implicit functions for shape, or in the case of, I guess, the sign networks, to be using what used to be called wavelet packets, right? And then fitting these. So, and there is a long history of using both in signal processing with explicit optimization algorithms, where essentially the capacity of those models is pretty well understood. Do you have any idea of what the capacity of the neural networks are? Like if I asked something to model a scene with a fence, or a sculpture that's a complicated knot, what size neural network would I need to have in order to feel confident that I would be doing a good job on the render end?
Yeah, that's a good question. I think the unfortunate answer is that this is not well understood. So in the case of value neural networks, there's some okay, there's some directions. Okay, maybe the highest level question is we don't currently understand this very well. I'm pretty sure in the next 5 years there will be better statements and better arguments that you can make. The current situation is as follows. For ReLU neural networks, we do have an understanding of how many hyperplanes you get for a given depth and width. So if you give me a neural network, a ReLU neural network, we know that the function that is parameterized by the ReLU neural network is piecewise linear. And in fact, if you see here on the left-hand side, when you zoom in on the car and you look closely, you can actually see these little piecewise linear facets on the geometry of the car. It's kind of a little bit like a mesh. It's called a Newtonian polytope. The topology of that. You can see it here. It's like piecewise linear. Right. So the number of these facets is computable. So I can tell you for a given ReLU neural network how many of these facets you have. However, that does not tell you, I am afraid, how you can arrange these facets in space and if you're actually going to find that solution in the first place. So that is still open. For ReLU, for these sine neural networks, there's no such statement whatsoever. However, there's another perspective that is being developed that is quite instructive, which is the perspective of neural tangent kernels. And there, I think we're going to get to some tractable statements within the next few years, where the statement basically goes as follows. What a neural network always does, in particular in this overfitting regime. So imagine you have a points in 2D and every point has some value and you're just fitting a neural network for regression, unlike regressing, mapping 2D coordinates to colors, for instance, like an image. You can show that in the limit of infinitely wide neural networks, the function that the neural network learns is identical to a kernel machine. In other words, the neural network is basically literally outputting interpolations of the training set for any coordinate that you sample thereafter. And the form of that kernel is defined by the architecture of the neural network. So in particular, for a sine neural network, you can show that as the frequency of the network increases, the kernel gets more and more peaky. And so the positions get decorrelated from each other. And that's why these neural networks are so good at fitting high frequency detail. While ReLU neural networks, it's basically a dot product kernel, which basically means that they will always basically blur and get this low frequency detail first. Now, these statements are currently not derivable for real world neural networks, but only for ones with infinite width or other approximations. But I think within the next few years, there's like hope that we will get to a tighter bounds on what these neural networks can do. This is an active area of research.
So this is something like a learnable random Fourier feature kernel or something like that, that you're learning the Fourier feature kernel using the sinusoidal maps?
So if the first layer of the neural network was sine activations, then it would be like a random Fourier feature kernel. If the whole network has sinusoidal activations, there is, to the best of my knowledge, currently no statement for what the kernel looks like. Practically, I think these networks empirically have been found to fit high frequency detail better and are more flexible and can decorrelate local positions even more. But I don't think there is a good statement for that kernel yet.
Okay, I see. Yeah, I've been playing around with your siren networks for quite some time, and one of the challenges is how you. Whatever I've seen is that there is a huge dependence on the number of periods of the sinusoidal waveform that you want to fit in. For example, you have some parameters like omega naught or something in your, it's quite sensitive to that. I mean, do you have any insights on how you decide on that, or is it just empirical?
Yeah, there is this insight with respect to the. So basically, what you do is if you increase the frequency, then you're making the kernel bigger.
Right.
And then how you pick like the relationship between the peakiness of the kernel and the frequency of the neural network is only understood in the case of the random Fourier features. Actually, sorry, even there it's not understood. Wrong statement, sorry. So even in the case of random Fourier features, currently there's no way of saying my signal has this spectrum, therefore I should pick a pick these hyperparameters. However, one of my collaborators called David Lindell has recently published a paper at CVPR, which is called Bacon, which is a funny name. But actually, it builds on some earlier work, which is called multiplicative filter networks, where instead of in fact having a neural network, it's kind of a low rank approximation of a Fourier series with lots and lots of terms. So imagine a Fourier series with like 1 million terms, but you know upfront that your spectrum is going to be sparse, so you can basically parameterize the spectrum low rank, and people have done that, and it works really well. And then in that case, the spectrum is actually closed form, it's analytical, the bandwidth at least of the spectrum. And then you can do the trick where you say, okay, I know my signal lives in this bandwidth, and therefore I'm going to pick my frequencies as such, and then I'm going to guarantee to stay in that bandwidth.
I see, okay.
Yeah.
So the compositionality, I think, is very interesting because it's one clear place where you might choose neural networks other than some essentially equivalent mathematical fittable function. And you went over that real quick. Could you give us some remarks on how it decides what part of the network or which representation to update? Essentially, there's a labeling problem. You have 4 chairs in a scene or 4 objects.
Great question. Yeah, this is a really interesting topic, and it's currently not. Let me go to the slide. I'm afraid the answer is unsatisfactory, but I'm going to. But there's lots of interesting remarks to be made. So let's go there. So okay, so the way this works is, let's say you have a given image of a scene that is compositional. So like in this case, you have these 3 objects here. Okay, so the model that we use for inference, which is basically the labeling problem that you just described, is a model that we didn't invent. It's called slot attention, and slot attention is basically a little bit like a vision transformer. But basically, what it does is it randomly initializes a set of vectors. So first, you take the image, you put it through just a pre-trained convolutional neural network that gives you like some feature space. Then you're going to randomly initialize a set of vectors, and these are the slots. You say, I expect a maximum of 10 objects. And then basically these slots compete for explaining parts of the image. I would defer you to the paper for how that works in detail, but basically it works by each slot in the beginning is randomly initialized, and it'll have a similarity to some parts of the image more than other slots. And then based on that initial similarity, it's kind of a little bit like a flood fill algorithm, where basically each slot will be attracted to the parts of the image that it explains best, and you iterate an algorithm a few times, and then you end up with these latent codes that basically explore the whole image. So in this case, you would end up with one slot that would explain the background, one that would map to the red object, and so on. In practice, that works for these simple scenes. It does not work for more complex scenes. And this is a known problem. There's 2 interesting perspectives on this. The first one, the queue, if you observe images and you are interested in reconstructing or solving this labeling problem of figuring out what are separate objects given just images, it's the only queue you can trust on is basically similarity across scenes. So if you see things that are similar across scenes, you can say, oh, things that are similar across scenes are likely to be the same object. And then you can use that as a cue to basically say, these things I would like to explain in a common space. In reality, that is.
Vincent, couldn't you recognize things that were similar across the same scene? I mean, like looking for regularities, like in the airplane, right? These scenes have the seats, right, within the scene have the similarity as well.
Yeah, no, I agree that I agree. Like if you know that in a given scene there's going to be the same object several times, then you could say we're going to look for a similarity in the same scene, and I think that would also be perfectly reasonable. The problem that you kind of run into is that that is a very weak cue. And we kind of know that there is a stronger cue for humans, which is motion. So the first kind of cue that you use for to disentangle objects is actually things that move together, belong together. And so one very interesting direction for this is, instead of looking at images, look at video where stuff moves, and then use the movement as a cue for saying things that are rigidly, like, in that way you can, in a principled manner, at least discover objects that are rigid. And that is something that we're working on.
So this the codes that you're learning here, is it 3D aware, or is it 2D?
Good question. Yeah, so these in this paper, this was basically this is the interesting part. So you get these codes, and that's not novel. Like, this is, as I had explained, this was proposed earlier. The thing that we do with these codes is cool though. Basically, each of these codes we use to parameterize a light field network, and that maps a ray to the color observed by that ray. And then we built this little compositor module, which is kind of like which basically takes the outputs of all of the light fields and then composites them into an image. And then you can render from novel perspectives. And so this has been done before with NURFs, so with like with these radiance fields, but it is really, really, really bad. Or not bad, it's great, but like it has huge downsides, which is, right, rendering a single ray for a single object is extremely expensive because you have to sample the same scene representation hundreds of times. Now imagine you want to composite something. Now it scales with the number of objects as well. So if you have a scene with 50 objects, for each point that you want to get, you have to query 50 representations, which is unbelievably expensive, so it doesn't scale. In this case, each object you have to sample exactly 1 point. So this thing, even if you have hundreds of objects, you can still render it in real time. So each of these little scenes here, that actually this I skipped over, but you have like this is like a larger scene here, where like still obviously very toyish, but it's a larger scene where you have like lots of these cars, and there's, you know, the city. This you can render with like 200 FPS on a single GPU, just because each of these objects you only have to sample once per ray.
I see. And how much of a data set do you need to train this?
I think it's on the order of like, for these simple room scale scenes, it's on the order of like, I think 2,000 of these rooms, something like that.
Okay, I see.
And you can kind of tell. So like this was kind of, I was really interested in like, how well does the slot attention algorithm do, because people have been using it, and I mean, it's cool that, I mean, it's great. It's a great algorithm. It was a great proposal, but you can kind of see the limitation here really isn't the expressivity of the light field network. The limitation is that if you make the scenes more complex, then your slot attention algorithm will fail to disentangle the separate objects. And that's why these have these bright colors and so on. Because if you're relying on similarity across scenes, then you're kind of a little bit lost.
Yeah, we had instance segmentation algorithm in ICCV last year, and one of the problems with slot attention that we tried to fix is this 3D awareness, and that time we used a 3D voxel representation, but I think like this your siren or the continuous representation is perhaps better in that sense.
Yeah, I think using like lifting these things to, if you have 3D available, if you have 3D available, then doing these things in 3D, I think is just strictly better. So I think that's a great idea.
Yeah.
All right, well, I think we are done for today. Thank you, Vincent, for really